Okay, good morning and welcome to today's confocal laser scanning microscopy seminar at the ABIF. So as I mentioned earlier, I guess we'll just be going through the basics of confocal just to give you a little bit of an idea of the scanning parameters to get you thinking about it, essentially to make it easier for your training once you have your sample. So I'll get going. So look, okay. So I'll be presenting this figure. This figure will come back a few times throughout the duration of this talk. So microscopy is a series of compromises. And essentially what this means is that, well, we always have to balance for any image that you're getting on any system. There's always going to be a balance of sample health, meaning the health of your cells and the lifespan of your GFP of your fluorophores, versus spatial resolution, so how fine you can distinguish two objects that are close together, versus the signal to noise, so how bright your image looks, and versus the speed, how long it takes to acquire it. Whenever you try to increase one of these for whatever reason, you will be digging into the other ones a little bit. So they're all interconnected, and getting a good understanding of this and of this with regards to your sample is critical to getting good images and getting images that that you'll be able to either quantify or get information out of, essentially. And understanding this in the context of the instrument is important as well, because, well, sometimes there's sort of hidden ways where you can kind of increase one or do things that are a little bit less destructive or faster or this and that. So we're always trying to balance these things and trying to get a good understanding of the instrument that we're using as well. So today we'll be talking about the confocal lasers. And essentially, the main idea why people use this is to try to remove out of focus light. And this is more important in thick samples, so more things like tissues or cultures and organoids that kind of grow into thicker sections. And so to give you an idea, this is simply a cultured cell that's stained for actin and mitochondria and DNA. And so this is an image on the wide field. This is an image on the confocal. There is a little bit of background blur from the wide field, which is essentially removed by the confocal, but it's not a huge issue. You can still distinguish individual fibers of the actin, and you can still clearly see the objects. Where confocal really becomes kind of useful and important is really for thicker specimens, as shown down here. So this is a 20 micron thick mouse kidney sample. And you can just see on the wide field, you do have this kind of this haziness, this blur, which comes from light that is out of focus, so that is just kind of blurring over the sample. Whereas in the confocal here, we managed to essentially remove that out of focus light using an optical trick involving a pinhole, which we'll discuss in a second. So of note, of course, this image, when you remove the out of focus light, it is much cleaner. You can clearly see everything is much more crisp. It's a much thinner slice of the image. It's nicer in a lot of ways. Kind of one thing to know, and again with the idea of balancing everything, is that you have to determine if this type of sectioning is absolutely crucial to your biological question, in that if you're simply interested in roughly the size of this entire structure, a wide field image such as this one on the left is totally fine. You'll be able to figure out the length of this or the width of this fairly easily. So, and the advantage to the wide field is that it will be a lot faster. This was probably just an image taken on a camera, probably took about 100 milliseconds. This was scanned on a confocal and probably took seconds to acquire. So kind of already starting to think, well, do I actually need this resolution for my questions, or can I get away with a hazier image? But let's look a little bit at the optical tricks that are carried out in the light path to generate this this out of focus removal, out of focus light removal. You already received your training on X/3, so on wide field. So we won't go over fluorescence directly, but we'll talk a little bit more about the light path involved in the confocal. So on the excitation side, we usually excite our molecules using a laser. And by using a laser, that allows kind of a high intensity and a very sort of narrow bandwidth, and allows us to get a nicely collimated light that we can really focus into a spot. So the light comes in collimated or parallel into the back of the objective lens, which is just shown here as a simple lens. And then the light is focused onto the sample. And I really want to stretch out that this is really just focused into a point, so nowhere near the size of the cell or the tissue. If you were to put a little camera down here, you would notice just one dot of laser intensity in the middle of a large sample. And so we'll talk about how to actually generate an image later. But really, we're trying to get the smallest point possible, which is dependent on the wavelength of the laser and the numerical aperture or some of the properties of the objective. So then, at this focal point here, where the intensity of the laser is the greatest, the intensity of excitation light is the greatest, you're going to have a collection of GFP molecules that are going to emit light in all directions. For the fluorophores, I should say, not necessarily GFP molecules, for the fluorophores that are at the focal plane of this objective, a collection of their a subset of their light will be collected by the objective, and if they're at the focal plane of the objective, they will emerge from the objective in a collimated orientation. So all these rays will be parallel to each other. They will then go through our dichroic beam splitter, essentially to split it from to separate it from our laser, and just keep the excited the emission light essentially. And then this light will then be focused by something called a pinhole lens towards the pinhole, which is very simply just a little hole in the middle of a metal disc, which we can vary the size. And this will just allow the light that's in focus to go through. So that's all very simple. And so how does that work for removing out of focus light? Well, we just talked about what happens when it's in focus. You have to imagine that throughout the path of this laser, there will be molecules that will be fluorophores that will be excited throughout the thickness of the sample. And so if you have something that is excited outside of the focal plane, so say at the top of the cell here, it is not at the focal plane of the objective, and thus the light, which you can see in these gray dashed lines here, will not emerge from the objective in a collimated orientation. So if it's closer to the objective, it'll be a little bit diverging. If it's further from the objective, it'll be a little bit converging. And thus, when it goes to the pinhole lens will be unable to focus it at the level of the pinhole. So that means that a large proportion of the light will be blocked simply by the metallic and opaque sides of the pinhole. And same thing if you have some fluorophores that are a little bit further, they will be converging, emerging from the primary objective, and they will be focused kind of earlier on. So again, we end up blocking most of the out of focus light by simply keeping what's in focus via this pinhole here. And so it's really the pinhole that allows only the in-focus light to reach the detector. So our detector is up here. And our detector is simply a point detector. So it's not a camera. It doesn't get a nice full camera with spatial, it doesn't get a nice full image with spatial information. It just detects how much light it can collect from a single point. And so we'll talk in a second about how to generate image of that. So it's with this basic principle of a focused laser and a pinhole that we get essentially the separation, that we get the removal of the out of focus light. So all this hazy stuff here from fluorophores that are out of focus is essentially removed by this the focusing only the in focus light on the pinhole. I hope that's clear. We'll see. So we'll go through the light path of how this works and how we actually generate an image out of this, so an actually image with spatial information. So we'll start here on the top left. So again, we have our laser. We'll go through a few iterations of these light paths just to kind of let it sink in. So we usually have a set of lasers. It's usually in a separate box called a laser launch. The lasers have a output intensity that we can then modulate or make dimmer using an acousto-optic tunable fiber. So this is how we adjust the intensity of the laser. And then it will go through essentially our primary dichroic mirror. And again, this is just to split the excitation from the emission light, which we'll discuss a little bit later. And then to be able to get an entire image, we have a set of two mirrors that are mounted onto galvometers, which are little devices that can oscillate a little bit back and forth or change their angle. So one about the x-axis and one about the y-axis. And by moving these back and forth, it will allow us to scan our point, our little laser spot, across our sample in both axes, x and y. And so over time, we'll be scanning and acquire the information of simply acquiring light from different portions of the sample. The light is collected by the objective lens and then goes through these galvo mirrors again, essentially for descanning, and then will be relayed back through the pinhole again to try to block the out of focus light. And then if we want, it can be split again with another dichroic mirror to separate. For example, you could have a GFP in the spectral range of GFP and in the spectral range of M cherries. You could have each could have a photomultiplier too, so a PMT. So it's really the action of these two mirrors that scan that point across the sample to generate an image. And we'll see this in two more cartoonish ways. So first we have this animation here. So again, the laser will be focused onto a point, but before getting there, the mirrors will kind of move back and forth, and this motion of the mirrors translate into a scanning pattern across the sample. So really going point by point, line by line, so in X and Y. The emission light is then descanned, so it goes through these mirrors again, and then is separated to get to the detectors via the dichroic mirrors, essentially. So you could be exciting GFP and M cherry here, and at the end, the GFP and M cherry via a second dichroic would be split onto two different photomultiplier tubes. Notice that there are different sort of arrangements to this. You could have one pinhole for all wavelengths, or different detectors could have their own pinhole. There are kind of different options for this, but yeah, this is still the main component of it. And so it's really this scanning that's happening. We're not taking a picture, we're really acquiring the light from different points over time. So again, very different from a camera, very different from the camera that you have on your phone or a camera that you would have on a wide field microscope. To see this conceptually in a slightly different way, essentially we'd have our lasers that are connected to the scan head, which is a big box connected to the microscope that has usually all the filters and the detectors and the scanning galvometers, and then an objective. The objective would then focus the laser into a point, which is again cartoonishly spot over here, and then with the galvometers, that spot will be scanned over the actual sample. So you can see this as an actual cell, an actual sample. And slowly the detector collects the light from each pixel, and then pixel by pixel, the computer builds up the image. And this detector is non-spatial, so it's only getting the light from one spot at a time. There's a change in voltage that happens that is then converted into a digital intensity. So then pixel by pixel, line by line, that image is built up. And so one of the reasons why we insist on sort of making sure this is clear and hoping this is clear, is that this allows a huge amount of freedom in terms of determining how you're going to acquire images. Essentially, you can tune via the speed of the mirrors and how much they move. You can decide essentially on how much spacing you want between these pixels. So you can choose the pixel size with much larger flexibility than you could with a camera, where essentially you have one or two pixel sizes available. If you want to change the pixel size, you would have to change the objective. Here you can just scan at different rates and within different geometry. You can also decide, I'm going to get a smaller image and only get this top section here of the cell. So you can choose to only scan a 4x4 or an 8x8 or whatever kind of format. So you have a great flexibility for acquiring, and we just want you to get an idea of how you can use this well, for the better, to get better images depending on what you need to see. So we'll go through a few cartoon case scenarios and then a few examples of what this would look like on an image. And this is really just to get kind of used to the geometry of confocal scanning. So we'll start with a cartoon. Here you would have a subdiffraction bead, so just a small fluorescent bead. And then on top of it, we'll just scan over it. So it has a certain pixel size of 250 nanometers. So every 250 nanometers, this is actually in time, not in space, but it will acquire the light. It will record the amount of light that was detected. You'll notice that in this cartoon, the blue lasery dot is a little bit shifted to the right. But we're slowly building up the image pixel by pixel, line by line. And so for something like this, we would get our resulting image, our resulting 3x3 image would be something like this. And here, of note, we can choose both the pixel size, so how frequently we're acquiring the information, and we can also choose our time, the time spent per pixel. So in this scenario, just as a cartoon, it's 1 second per pixel. In reality, it's more on the microsecond time scale, but we'll get to that in a second. So here, if we were collecting these 9 pixels, we'd get this image here, and you'd have to ignore that spot in the back. So it would look something like this. So then what happens if we change our pixel size, or we increase the sampling frequency within this same area here, but we leave everything else the same, so same scan time, of course, same laser intensity. So that would mean that we would get, well, an image that looks like this. Essentially, we're scanning more often, but still at 1 second per pixel. So you end up with, as you can see right now, a much slower scan, right? And the reason for that is simply that we're acquiring, well, 2 times more pixels in X and 2 times more pixels in Y, so 4 times more pixels in total. So that means it'll take 4 times the amount of time to acquire. While this is simple kind of one scheme like that, you have to think about this if you are acquiring Z-stacks in 3D, because this will affect essentially how long you have to spend in the microscope. And so there we go. It has scanned. And so this is the resulting image. If we kind of compare the two, again, this would be our bead and this would be to scale. We simply acquired 2 times more pixels and we get kind of a higher resolution. It's easier to see the information here. But the slower scan means that there was more light that was shined onto the sample. So the sample received more light. And so there was a greater risk of photo bleaching and phototoxicity. If we just compare these, the numbers, well, the pixel size is reduced by half. So again, slightly better resolution. But due to that half and that it's squared essentially because it's an area, then we end up with 4 times more, it takes 4 times longer to acquire that field of view. The time spent per area is also 4 times higher, and thus the power density per area is also 4 times higher. So there's greater risk of either photo bleaching or phototoxicity here. And to give you an idea, the signal to noise, since we kept everything the same, is about the same. Right. So again, this is an idea of balancing. If you can get away, if this level of resolution is enough to answer your biological question, then this is going to be better for the cell, and it's going to be faster to acquire. If you really need the higher resolution information, that's totally fine, but you have to be aware that it will take longer to scan. And so you have the flexibility to choose between this, and of course we went from 300 nanometers to 150 nanometers, or we changed by half. You can make it slightly smaller, and you can increment this essentially almost as much as you want. So it's important to kind of think about this and really get the resolution that you need, and not simply the highest resolution possible if it's not necessary. And so we'll give an example of what this would look like on a microscope with, again, the kidney slide. And so we'll have 3 different scan settings. All these settings are things that you can adjust directly in the microscope. So here's an example of, well, the image size is going to be 159 microns for all of them. So we're going to get the same chunk of tissue for all 3 images. We're going to keep the same pixel dwell time, so 2.06 microseconds per pixel. And the only thing that we're going to be changing is our frequency of sampling. So here we're going to get 512 by 512 pixels, 1024 by 1024, and 2048 by 2048. So in essence, what's going to change is what we talked about earlier, is that there's going to be a change in the time it takes to acquire a frame, which is shown here, and of course the resolution. So if we just show this, I think we have our animations kind of tweaked for this, which is kind of cool. It's going to be very fast to get this first frame. Of course, this is just animated in PowerPoint, but it would be 1.27 seconds. Then slightly higher sampling frequency, go to about 5 seconds to get that 1 frame. And then if we again get a higher sampling frequency, it's going to be much slower. It's more around 20 seconds per frame. So a huge difference from 1.27 seconds to 20 seconds, depending on the resolution that you want. Now, where it's important to notice is that I'm guessing for you, especially over Zoom, and even me on my screen, I cannot see an actual difference between these images at this zoom, right? It's only if we zoom in that then we clearly see a difference. So here, because we have more pixels acquired here, or a greater sampling frequency, of course, this is a much finer image. And so this is really nice, and this is great, and this is of course more visually pleasing and more informative possibly than this. But then it depends on your biological question. If you're looking at stuff that you need this information from this small structure, then this is great. If you're really only interested into how many of these tubules exist in this slice of tissue, or generally the expression level throughout different tubules, then this resolution might be enough, and thus you'll be able to scan your samples much quicker. And so it's really important to know what you're looking at, what is the spatial scales of the structures that you're interested in, to be able to make this choice, because this is literally a 16 times difference in acquisition time. And so that goes from 1 hour of scanning to 16 hours of scanning is definitely worth considering and fine-tuning. So again, this comes back to balancing all of these things, the speed, the signal to noise, the spatial resolution, and the sample health. So maintaining your fluorophores, unbleached if you're sampling them, if they're fixed, and of course maintaining both the fluorophores and the cells alive if the cells are alive. And this kind of sort of further highlights the need to really know what you're doing and really, really narrow down your question. What are you looking for? And not just try to get the highest resolution possible without thinking it through. It's possible that your question requires the highest resolution possible, but you just have to make sure that it is. Otherwise, you will be spending a lot of time at the microscope, and you might be getting data that is not valid or is not useful. So we'll go through a couple of other sort of cartoon examples, and then a little bit more on the microscope. So in terms of the geometry of the scanning, we can change, of course, the sampling frequency. We can also change the speed of the scanning, so how quickly the laser is scanning across, and thus how much time is spent per pixel. So what is the dwell time? So if we just get this going, well, here we can go much faster. So we can say, let's spend 1/4 of a second per pixel instead of 1 second. And of course, it scans much faster, which is great. But this will lead to a decrease in signal to noise, essentially, because you're spending less time acquiring light. It's kind of analogous to an exposure time on a camera. A longer exposure time, you're collecting more light. But on the other hand, since you are going faster and spending less time on the sample, well, then you're reducing photo-bleaching and phototoxicity. So again, you have this sort of trade-off between going quickly, scanning quickly and scanning slowly, again at the same, in this case with the same sampling frequency in terms of pixel size. So we change our pixel dwell time, we have the same pixel size, the time per field of view is shorter here. Our power density is also lower here, except our signal to noise is going to be much lower. So for the same object, you would get a much dimmer image, or much more an image where the signal is much closer to the noise. So it's a little bit more difficult to, it can be more difficult to analyze. So again, it's going to be a balance of exactly what you need to see within the time that you have to acquire it. Right. And this is again compared to what we discussed earlier, which is just getting a lower sampling frequency. So here you kind of have this in between where it's faster but lower res. So all these kind of things to kind of balance essentially. Right. And so again, just in thinking about this, well, you can really, all these things are tunable. It's not one or the other. So you can try to push and pull. It's a little bit more continuous in that sense. You can look for things where you have kind of a low power, but high resolution, but low signal to noise. Here we have low power, low resolution, but high signal to noise. We have high power, high resolution, high signal to noise. And so you have, these things are going to be slower to acquire or take more time to acquire, but they're the highest resolution. But of course, you risk photo bleaching, you risk photo damage, and of course, they do take a long time. So again, thinking carefully about what you're doing essentially. And I come back to this all the time because it is important. We often refer to this as the pyramid of despair, but it's always just these compromises. And again, just further highlighting, it's probably not great to just go take pictures for the fun of taking pictures. It's really go in with a question and get the, do the compromises that are needed to address that question rather than try to catch everything at the same time. So very often you'll have very, very different acquisition parameters depending to answer different questions that might all still be within the same project or the same paper. But that's it, do some fast stuff for some fast questions, do super high resolution for very, very intricate stuff, and do kind of lower resolution for more global things. So really trying to, you'll have really different data sets, and it makes the acquisition a lot easier if you have one question, one set of structures that you have to balance, and not try to get something that is both, that is all multiple things at the same time. All right, so we talked about the scanning geometry in terms of speed of acquisition and photo bleaching. We'll just talk about the geometry of the scanning a little bit more in terms of what is the size and the shape of the image and how you can play with it a little bit, or kind of thinking it from a different point of view. So here we're talking about a little bit more about the field of view. So we'll always be acquiring an 8x8 square of pixels. And we'll change one of these parameters, either pixel size, the size of the field of view, or the number of pixels. We'll hold one constant and see kind of what changes. And so everything kind of follows in that sense. Right. And again, this is always going to be with the 8x8, and that has a certain size. So then what happens if we keep the pixel size constant? But we actually change the number of pixels. So we can actually just say, oh, instead of scanning an 8x8, I'll be scanning a 6x6 with the same pixel size. Then what we do is that we change the field of view, right? So this is known as cropping or scan cropping. And this allows you to simply, well, just get an image of a smaller region of your sample. And so how this looks, suppose you have this whole sample. You would just say, oh, I just want to scan in this area here. And that's it. And because you don't need the information on the outside for whatever reason. And so you're just going to say, oh, let's just get this. And this allows you to go a little bit faster. And so you get no change in resolution, but you get faster scanning, no increase in light power or light power density, and no increase in photo bleaching, because if you're just changing the number of pixels, you're not changing any of the density or anything like that. So what this means is, well, smaller number of pixels to acquire, a smaller field of view, equal pixel dwell time, because you haven't changed anything there, a shorter scan time, the same power density, and the same sampling frequency. So again, we just took this image and chose an inner set of it. And again, this is cropping. Conversely, what we can do is keep the number of pixels constant, so do an 8x8, but then reduce the pixel size of each of them, and still do an 8x8, essentially. So here what we do is that we actually reduce the field of view, and sort of what else changes? Well, this is known as scan zooming, and so here what we're trying to do, we're actually changing the resolution. And so in this case, we're actually increasing the resolution because we're getting a higher sampling frequency, but we're also increasing the light power and thus increasing the risk of photo bleaching and phototoxicity. And so for something like this, it'd be like we're choosing a region, but we're getting a higher sampling frequency within that region. So we're still only getting a subset of that whole chunk of tissue, but here we're getting at higher resolution. And so this is really known as zooming, comparatively to cropping. And so here, your number of pixels is, well, same. Your field of view is smaller. The pixel dwell time is the same. The scan time is the same, so you don't save on time. Your power density is higher because you're acquiring a higher sampling frequency, essentially. And so it's kind of important to have an idea of how you can play around with this geometry of scanning, both in terms of the dwell time, the number of pixels, and also just how you can sort of modulate really the size and the geometrical aspects of your scanning kind of as you want. On the confocal, you have much more flexibility than you do on a camera-based system, but you have to really have an idea of what you're doing and how it might be advantageous to your imaging. And so again, this comes back to the idea that you're scanning point to point, so you can really modulate all the aspects of the speed of the scanning and the amount of time spent on each pixel, the amount of pixels, the range that it's scanning in, every single sort of geometrical parameter that you can think about here, you can and probably should modulate for your needs. And so I'll stop with discussing scanning for this. I'll just talk briefly about detectors. And this is just, again, to remind you that it is different from cameras. So we do not have cameras on confocals. We have point detectors, either photomultiplier tubes or avalanche photodiodes in most cases. And this is just kind of give you an idea of how this works. So again, this is a non-spatial detector. So it only detects the amount of light. It doesn't have any information of space. The space comes from the scanning. And so for something like a photomultiplier tube, which is kind of a classic that we have on a few of our systems, you essentially have these charged dinodes that act as amplifiers. And so from an incoming photon, will go through the photocathode, will be converted to an electron, and then as it hits these charged dinodes, every time it hits this dynode, the dynode will then kind of emit, well, in this case, it's cartooned as two, but a couple of electrons, and then this will be amplified throughout this kind of chain until it's actually detected on an anode, so after multiple rounds of amplification. Here it's always schemed as, 1 gives 2, and these 2 will give 4, and these 4 will give 8, etc. It's a little bit more noisy than that, doesn't have that efficiency. There is a stochasticity to it, so they can be rather noisy, but they are very, very fast, and they're very good amplifiers. So by using these can operate at rates that make sense for us. So on the microsecond timescale per pixel, so microseconds are super, super short, but then if you're doing a 1000 by 1000 pixel image, which is somewhat standard, that means that'll take, well, 1,000,000 microseconds, so around 1 second. So this is how your acquisitions can easily be on the seconds timescale for a whole image. And it's thanks to this type of technology. A camera needs a minimum of usually around 5 milliseconds to take a picture, so you would not be able to take 1,000,000 tiny pictures so quickly on a confocal. And this is really just to stress that you're only getting the information from 1 pixel, and thus you do this thing will measure the first pixel, and then as your laser moves around, we'll get the information from other spatial areas, and slowly the computer will then rebuild the image from that sequence of light measurements, if you will. Of note, as you're preparing your samples, different detectors have different spectral sensitivities, and actually most components of the light path do have a spectral width of efficiency. So it's important to kind of choose your fluorophores in terms of what detectors are available in the system, and you can talk about that a little bit more when you have your training. In most cases, because most people will use things going from DAPI to things like GFP to things like TRITC and to things like TRITC and things like Sci5, most of the detectors are set to sort of work in that range. Some of the gas detectors and other photodiodes go a little bit further. So if you're doing like IR or very, very far red stuff, kind of be aware that the efficiency can drop down a little bit. And so if you're deciding which target to use with which fluorophore, you might want to keep this in mind. If something is very dim or very lowly expressed, it might not be ideal to use the far red. If you can swap it with something else, and use the far red for something a little bit more structural and more densely labeled and things like that. So just stuff to be aware of. And finally, I'll just show these very quickly, but you'll discuss these more in your talk. So if you're being trained on one of our Zeiss systems, of course, there's a schematic of the light path for the Zeiss, where you can go through the kind of the whole light path. There's spectral detection on the LSM710, which allows you to get information from different wavelengths, or different ranges of the spectrum, essentially, without the use of filters. So we won't go this in particular, but you will go through this with you'll most likely go through this with your trainer during your training. And so we have this for the LSM710, and it's a different light path for the Leica. It's all based on a similar thing where there are scanners and pinholes and all that, but it is important to have an idea of, a little bit more closely how the system you are using is actually functioning to be able to actually adjust it properly. And so that's it. Again, I hope we sort of drove home a little bit how the pinhole works, how you have kind of quite a flexibility in terms of the scanning geometry, and hopefully how that that will modulate the quality of the images and the quality of the information that you can get out of it. And of course, this is all based on what I really, really hope everybody knows is this triangle or pyramid of despair, where you're always trying to balance these things to answer a question. So if you can really focus on one question per experiment, you'll be able to get better data. If you need to look at multiple things at the same time, then it becomes a compromise. And yeah, so it's a lot to balance at once, but hopefully you'll be able to kind of optimize to get the best acquisition parameters. So that's it. I will stop sharing, and we can get to questions.